Welcome to Chapter 2, Dealing with Measurement and Problem Solving. The skills we will develop are how to read measurements correctly, how to use scientific notation, how to report quantities with the right number of significant figures, how to count significant figures, how to round numbers, and how to do calculations that give results with the correct number of significant figures. Consider a meter stick. A meter stick contains 100 centimeters. The portion shown here is the part between 50 centimeters, 51 centimeters, 52 centimeters, and so on. There are 10 spaces, or 9 marks, between the 50 and 51 centimeters. So each short mark is worth 1/10 of a centimeter. The correct and accurate measurement with this meter stick will include an estimate of the distance between 1/10 of a centimeter, which would be in hundredths of a centimeter. Measurement C appears exactly on the 50 centimeter mark, but it should be recorded as 50.00 centimeters to the hundredth place. B is nearly halfway between the 50.5 centimeter and the 50.6 centimeters. It should be recorded as 50.55 centimeters. And finally, position A is nearly to the 51 centimeter mark. It is considerably above the 50.9 centimeters. Let's say that it's about 8/10 of the way to the next mark. So we would record this as 50.98 centimeters. The uncertain or the estimated number is the last reported digit, and it is significant. So all of the readings given here have 4 significant figures. Scientific notation is convenient for writing large and small numbers. A number written in scientific notation has 2 parts. A decimal part, that is between 1 and 10, and an exponential part, in which you have 10 raised to a power, or an exponent. Scientific notation that have positive exponents are large numbers, and it means 1 is multiplied by 10 as many times as the exponent. Negative exponent means theirs are smaller than 1, and it means that 1 is divided by 10 n times of the exponent. Examples: 10 to the 2 is 1 times 10 times 10 2 times is 100. 10 to the 3 is times 10 3 times, or 1,000. On the other hand, 10 to the minus 1 is 1 divided by 10, and it's 1/10. 10 to the minus 2 is 1 divided by 10, and again divided by 10, or 1/100, and so on. Let's consider converting some numbers to scientific notation. For instance, 5,983. If we look at this number, we see the decimal point would be located here, and we move it 1, 2, 3 times. This indicates that for scientific notation, we'll write this as 5.983 times 10 to the positive 3. Moving to the left gives a positive exponent. Again, we might look at 34 10,000ths, which we would move the decimal point 1, 2, 3, 4, and record 3.4 times 10 to the minus 4. Moving to the right gives a negative exponent and a small number. Now, still easier yet would be to enter these numbers and press second and then SCI, which is above the 5 key on your TI 3130 calculator, and you should get these results on your calculator. Significant figures are reported so that every digit is certain except the last, which is estimated, but it is also significant. The greater the precision of the measurement, the greater the number of significant figures. So this particular measurement has 5 significant figures. How do you count significant figures? Well, first of all non-zero digits are significant. It's the zeros that might give some pause for thinking. Interior zeros, or zeros sandwiched between two numbers, they're always significant. Trailing zeros, that are those that lie on the right side with no numbers following them. If there is a decimal point in the number, they are significant. Trailing zeros that fall and there's no decimal point in the number, they're not significant. They're merely placeholders. Leading or preceding zeros, those to the left of the first non-zero digits, are not significant. They only serve to locate the decimal point. They're placeholders. So in summary, all non-zero numbers are significant, and zeros sandwiched are always significant. Preceding zeros are never significant, and trailing zeros are only significant if the number has a decimal point. Otherwise not. Let's try some examples. How many significant figures are there in each of the following numbers? This particular number has preceding zeros, which are never significant. So it has 2 significant figures. This number has a sandwiched zero and a trailing zero and a decimal point. In such case, all of these are significant. So we have 4 significant figures. This number has all non-zero digits, and they're all significant. 4 significant figures. This is scientific notation. The decimal part of the scientific notation has all of the numbers, even zeros there, are significant. So this has 3 significant figures. This is a dozen, a counting number, so it's exact, and it has unlimited significant figures. This number has trailing zeros with a decimal point, therefore all of the zeros are significant, and the 1 giving yourself 5 significant figures. This number has trailing zeros, 5 of them, but no decimal point, so it's ambiguous. If there were a decimal point placed here, it would have 6 significant figures, but since there's no decimal point, perhaps it's only 1 significant figure. What are the rules for rounding to the correct number of significant figures? When numbers are used in a calculation, the result is rounded to reflect the correct number of significant figures given by the data. For calculations involving multiple steps, round only the final answer. Do not round off in between steps, because this will cause you to have some rounding errors in your final answer. How do you round? Well, you locate the last significant figure to be recorded. Then you look to the right of that digit, and you leave your significant figure as it is if the number to the right of it is less than 5. But if the number to the right is greater than 5, you round up. The digit becomes 1 larger that you record. If the number is exactly 5, then some people keep the digit as it is if it's even, or they round up if it's odd. You can do this if you wish. How do we know what are the number of significant figures to use in calculation? Most of our calculations will be multiplication and division. So the result should carry the same number of significant figures as the factor with the fewest significant figures. Here we have an example. This example has 3 factors, this one, 2, 3, and the number of significant figures in each factor is given. If you enter the calculator, your calculator will present you with this result. However, it has too many figures. It should have only 2 significant figures because this factor has only 2. So we need to look at that, and we see that 45 is the last significant figure, and we look to the right, it's less than 5, so we do not round up, we just leave the answer at 45. Here's another example. Again, we have only 2 factors, and we're dividing this time. The calculator gives us the answer 0.96590, but looking at the factors, we see that 3 significant figures should be in our answer. So rounding this to 3 significant figures, we work on this. We see that this should be the last recorded figure. However, the digit to the right is a 9, so we're going to have to round this 5 up. And so the answer is 0.966. 966 thousandths. Significant figures in calculation. In addition and subtraction is a little bit different, and we won't be doing as much of that, but it simply says that your answer should have the same last place of significance as the term with the highest last place of significant figures. And you can see that the hundredths place here, the thousandth place and thousandths place, so our answer should have only the hundredths place. Sometimes it helps to draw a line. And so do your addition and subtraction, and this answer is 9.214, but we see that this should be the last place of significance, and so we round it, seeing that the 4 is less than 5, to 9.21 as our answer for this addition and subtraction. What are the basic units of measurement? The international system of units are called the SI units, and the most important ones, there are some others mentioned, is the measurement of length is the meter, measurement of mass is the kilogram, the measurement of time is the second, and measurement of temperature is Kelvin. In the metric system, we have prefixes that indicate the multipliers. And the prefix tera, capital T, indicates multiplying by 10 12 times. The number is 1,000, a million, a billion, trillion. So numbers in the trillions are tera. They have the prefix tera. Then we have the prefix giga, capital G, and 1,000, a million, a billion. They're in the order of magnitude of billion, 10 to the 9. And the mega is in the order of magnitude of a million, capital M. You notice the bigger numbers have capital letters for their abbreviations. And then we have the standard unit of the SI system, the kilogram, or the K, which is 1,000. Then the deci is a tenth, the smaller than 1. And centi is a 1/100th. Milli is 1,000ths. Down all the way down to micro, which is a Greek letter, and nano, 10 to the minus 9, pico, 10 to the minus 12, and femto, 10 to the minus 15. In chemistry, we deal with measurements all of this magnitude, this range of magnitude. How do you choose the prefix multiplier that's most inconvenient for a particular measurement? Well, generally you pick a unit size similar or smaller than the unit you are measuring. For instance, you know that a chemical bond is 1.2 times 10 to the minus 10 meters. In the range of prefixes, you have nano, which is 10 to the minus 9. That's bigger. And you have pico, which is 10 to the minus 12. That's a smaller unit. So which prefix should you use? Well, you probably should use pico. So to get pico, you have to multiply this, divide this by 10 and get 10 to the minus 12, and multiply this part by 10 and get 120 by 100. And so you have 120 picometers. Or it could actually be 12 hundredths nanometers. We have derived units. Derived units are formed from other units. For instance, volume is length cubed, and area is length squared. A unit of length is squared is an area. The unit of length cubed is volume. These are square inches, square centimeters. They're measures of area. And cubic centimeters, cubic meters. These are all units of volume. We are going to be involved in unit conversions in our problem solving. So this is a good time to get the basics important. We must label all numbers with their correct units, and we must use dimensional analysis in order to get the desired answer result in the desired unit. So generally we'll have some information given that will have a given unit, and we'll have a conversion factor that is a relationship between the desired unit and the given unit, and we arrange it in this manner so that the given unit is canceled and get transformed into the desired unit. For example, convert 44.7 centimeters to inches. We're given 44.7 centimeters, and we know from the conversion factors that 2.54 centimeters equal to 1 inch exactly. So we will put the 2.54 centimeters down below in the denominator, so it will cancel this. The units will cancel, and we'll then put the 1 inch in the numerator, and we'll carry out this division. 44.7 divided by 2.54, and it will give us a number that will be showing the number down here. It's pretty many numbers. It's 17 point all of those numbers. However, the significant figures should always be equal to the significant figures in the given quantity. So since this has 3.6, this has 3 significant figures, your answer should have 3. The result then is rounded to this correct answer. You might want to try this on your calculator and see if you get the same result. It's important that we think about solving problems using conversions, and for this we're going to use a very important concept called a solution map. We're going to have where we start here in a purple box, and where we're going with a equality or conversion unit being used to be informed either as a fraction with the wanted unit in the numerator. This example is we're going from inches, then we multiply by 2.54 centimeters per 1 inch. Inches cancel, and you end up with centimeters. Or vice versa. If you're going from centimeters to inches, the conversion unit is inverted with centimeters in the denominator, 2.54 centimeters, to get the desired result. Our general problem solving will be we identify the starting point, what is given, would identify the end point, what you must find, and we'll devise a way to get from the starting point to the end point using what is given or is also what you know or you can look up. You can use the solution map to diagram the steps required to get from the starting point to the end point. So in graphic form, there's a given, the solution map, find. So to really solve problems, we need to sort the information in the problem. We have to develop a strategy and draw a solution map, and then we carry out the mathematical operations, paying attention to the rules of significant figures in the calculation, and we cancel the units as needed. Finally, we check our answer. In multi-step conversion, each step in the solution map should have a conversion factor with the units of the previous step in the denominator and the units of the following step in the numerator. And all the conversion factors are equalities that you find by definition. So centimeters to inches, this is the conversion factor in that order. And then inches to feet, this is a conversion factor in that order, arranged so that the inches cancel and the result is feet. Once the solution map is completed, you simply put in the numbers to solve them. So here's an example of converting 194 centimeters to feet. This is entered, of course, in your calculator. You have to remember 194 divided by 2.54, and generally I say press equal and then divide it again by 12 because it then is clear that you're dividing the answer by that, not dividing this denominator by that. So anyway, check this out on calculators. Make sure you get the results, 6.3648, and round it to 3 significant figures because the given is 3 significant figures.